imaginamento óptico, né, e além do visível e aplicação biomédica do infravermelho de ondas curtas. Você a palavra.
Muito obrigado. Eu não saberia traduzir, na verdade. E aproveitando, deixa então primeiro para agradecer o convite. E eu vou apresentar em inglês, espero que seja tudo bem, porque os termos estão falando do Silvio antes, que até espalhamento. Eu descobri essa semana que era espalhamento, scattering. Então, vamos lá. So, a little bit about myself. I actually studied marine biology in Imbé. And for 1.5 to 2 years, I studied a bit of marine mammal ecology, but then I actually wanted to do some experimental research, and then I joined the Department of Biochemistry. We were first working more with cells, glial cells especially. Then I went more to work. I went to work with the mice, so doing some behavior. Then I worked with Professor Marcelo Dietrich from Yale University, and then it was kind of my first connection to doing research abroad. And then I did my master's still in the biochemistry department, but then most of the time I was actually in Portugal doing research there, working with adipose tissues, so with fat and neurons, innervating the adipose tissue and promoting weight loss or body loss, fat loss. But then my passion for imaging actually sparked, and I was exposed to a number of different techniques that actually made me more interested in solving this kind of problems, troubleshooting the systems, and understanding the technicality and their applications to biology, rather than asking my own biological questions. And that's what motivated me to apply for the PhD position with Professor Oliver Bruns. We started in Munich, and 2 years ago we moved to Dresden in the National Center for Tumor Diseases. So Dresden is a beautiful city in the east of Germany. It's a historical city. Actually, all of this was flattened in the Second World War with the bombing, and all was rebuilt. It's a really cool city. It's quite small for our standards, about 300,000 people, but it's a cozy place. And this is our building of the National Center for Tumor Diseases, and it's a really good atmosphere to foster innovation in both treatment and detection of tumor. And our department is the functional imaging in surgical oncology. This is an experimental OR. We have this OR in our building. It's mostly for large animals, and you have like high-end imaging devices. We can take our own imaging devices and test in the animals. And so it's basically the first step before translation. So let's start. First, this electromagnetic spectrum. Many regions of the electromagnetic spectrum are exploited for medical imaging, ranging from X-ray, and then in the visible we have surgical guidance and thermography, and loads of other techniques that you're well familiar with. And I would like to focus and introduce the shortwave infrared that here we'll call it shortwave infrared. Some people, some authors call it an NIR2, and it's here for this talk, for this purpose. It's the region between 1,000 and 2,000 nanometers. So I'm even making myself uncomfortable in the physics department talking about astronomy as a biologist. But well, this is a nebula in the visible, And there are actually a number of stars underneath all this nebula, but it's not really visible. And when you image in the shortwave with bandpass filters in the shortwave, these stars become visible. And that's because scattering is reduced in this wavelength. In addition to astronomy, SWIR imaging is also was particularly in the past was used for defense to see through fog. Now there's new technology, and that's a reason why the shortwave infrared detectors were mostly restricted for military use. And the novel biological applications are coming up or have come up in the past 2 decades, basically. So I talked about scattering, and before going to mice, we'll quickly talk about water absorptivity. And in a certain bands in the shortwave infrared, highly absorbed water to the point that water becomes black. Here we have a leaf pretty opaque at 1300, and then when you place a filter at 1475, the vessels of the leaf become with high contrast. They become dark. And what the work developed before my supervisor became a PI, a principal investigator. One of their work was actually developing a device to image middle ear fluid, which is present in middle ear infection. In the visible, we see the pretty opaque fluid, and in the SWIR, it's pitch black. So they developed this otoscope, and the video played too quickly, but we'll see now. We'll see now when we have the stills. But basically, there was not much of a change in the visible the moment the now it's running. The moment we image the fluid in the SWIR, it goes from white to black. And here we have the still seeing that the contrast was increased, label free, just by imaging water, putting a camera facing the setup without any illumination, but the wavelength that you actually want to image, the reflectance. Okay, but I'll start talking about fluorescence actually. And this is the image of a mouse with indocyanine ring. So it's ICG, it's cyanine, of course, from the name. It's a clinically approved NIR, near infrared agent. And to the left, we see how it's actually the contrast we get at the peak of its emission. When we image the same mouse, the same molecule with a long pass, 1300 in this case, the contrast remarkably increases. Now we're imaging the tail of ICG, 500 nanometers to the red, and the contrast is much more remarkable, visualizing structures that you couldn't see before, like now with in the lower limb, that the vessels. It's not really clear, but maybe for people on YouTube, the vessels here on the right, they start to detect, but it's absolutely not visible, not detectable in the NIR. And this effect comes from a combination of the reduced scattering and the higher water absorption that we talked about. Another effect is the translucency, or how translucent skin becomes. And now we can clearly see the vessels under the skin and the vessels on the skin as we move it around. Again, imaging at 1300 long in INGAS. I didn't really mention, but of course, the silicon detectors do not really detect above. Few will do, but typically do not detect above 1,000 nanometers, requiring special detectors such as indium gallium arsenide, INGAS, which we use in this case. So, one of the purposes of our department is to move all these things that we developed, all these advancements, towards the clinic. So what do we need for the clinic? First of all, we need clinically safe contrast agents and clinical imaging setups. There are no shortwave infrared imaging setups, only NIR. So ICG imagers, for example. One option is simply imaging the tail of ICG, like I just showed that it's possible, but it's remarkably suboptimal because we're just detecting a little bit of its signal. So materials that have brightness with improved performance in the shortwave should be characterized, should be synthesized. And for that, we collaborate with particularly 3 groups of chemists: Professor Alan Slatton at UCLA, Martin Schneemann at the NIH, and Oliver Plettenberg in Hanover. Let's start with the Slatton group. So in 2017, while Professor Brings was still at the MIT, they published this dye. They called Flav7, so it's a flavinium scaffold with pure absorption and emission in the shortwave infrared. It was the first polymethylene of this class. And it actually sparked a lot of research in this area. And now we're talking about stymine, so the same class of ICG that is clinically approved. So you have a good starting point for safety. Of course, you need to perform all the toxicology and the tox. There's another one to do as well. Well, that's a good starting point. It turns out it's pretty hard to redshift more. They are now publishing it, but in the time 5-6 years, mostly what we built is the library of probes with SWIR emission, but with shortwave infrared emission, but with excitation between 800 and the 1050 that Flav7 already had. So yeah, there are 2 strategies to redshift the dyes. One is extending the polymethylene chain. The second is choosing heteroatoms or heterocycles of desirable photophysical properties. And I'm throwing a few buzzwords here, I guess, more than definitely not chemists. But now we have this library, and by the way, it's actually pretty bright. The probes are pretty bright. Here we're imaging at 3 milliseconds, 300 frames per second. This is a slow down movie of the mouse freely moving, and you can appreciate the vasculature in the head, in the back, and around the neck, while the mouse is moving around without much blurring, without many motion artifacts. So it's pretty bright. That enables you to image fast. Not all probes, of course, are this bright, but it's, again, a good starting point. So there's this library of dyes. We then choose the lasers to match their excitation maxima. Then we simply trigger the lasers. We do sequential acquisition. That's one strategy that we do. Then, yeah, I'm talking about lasers, but they will go, they will be fiber coupled and then diffused. So it starts at 40 watts, but then at the level of the mouse, you have 100 milliseconds. 100 milliwatts per centimeter squared. So pretty much 1 sun. And then on the detection side, because of the water absorption, different images will actually give too much chromatic aberrations. So we focus on imaging in a single window, usually with a long pass. So multiple absorptions, single window, and that also enables us to image fast, because we don't need to change the filter, even though, of course, there are fast filter groups. There will be a better drawing later on. Well, this is a mouse, an anesthetized mouse with an injection of 1 probe in the intraperitoneal space in the belly. And then we can play with the biodistribution of ICG. ICG is cleared through the liver into the bile and then the intestines. And we're seeing now the intestines of the mouse combined with the peritoneal space. And then there's a third probe that was injected 1 day before that is cleared by macrophages, and then it's present in the spleen and the liver, in bones and the lymph nodes. And there's a fourth probe now being injected, and then showcasing that we can do four-color multiplexing in the SWIR in kind of real time, 25 frames per second. Yeah, you can also let the mice wake up, move around. This is not the prettiest video, but we have a nice project of extracting quantitative information from the mice moving around, because it's challenging to, if you want to do quantification and the mouse moving around, it will depend on the position, the signal, the absolute intensities will be very variable, but now we can combine two channels. One is stable, the other one is dynamic, and we use that simply as a ratio to account for the motion and different positions. But I'll not get into details. That's just in case anyone wants to talk about it later. So, quick water break. I think I'm actually going really quick. So, these probes were all passive targeting. They were not targeted, they were not conjugatable. We simply played with the biodistribution. We could play with some micelle formulations to increase the blood circulation time. Then we have a nice application in geography, for example. But this is a work developed by Professor Martin Schneemann at the NIH or NCI. And I'm not part of this study, but I think it's a nice closure to the fluorescence and to the fluorophore topics. It was also developed by our group, but it was just another biologist in the team. And now they developed two conjugatable, very redshifted dyes, one at 872 excitation and the other one at 1072 excitation. And in this case, we'll show an application of fluorescence-guided surgery in which we have panitumumab, so an antibody conjugated to the dye, targeting the tumor, that's in red. ICG will have passive labeling of the lymphatic system. There's a dextran conjugated to the FNIR 1072, labeling the blood vessels, also for longer circulation, and in gray, some reflectance to give good perspective to the surgeon. This was actually also, in addition to the chemistry, it was a nice computer science project because it's, if you just acquire the data, the images would come sequentially, so you don't see them in this in this situation. You get the multicolor only after processing. But he developed the method that the surgeon was dissecting this tumor here in red while looking at the screen. And that was, yeah, a cool project, also highlighting the interdisciplinarity of what we do here, and for sure what you guys do as well. So the tumor was removed. It might take a second more, and then you can also dissect the lymph node, because for the surgeons it's important to find the lymph node through which the tumor is drained to see whether there are tumor cells there. And in this case, there is some red signal in the lymph nodes. We haven't gone through histology. This actually, we basically realized afterwards, after the paper was published. But that's something for sure to confirm, because it could simply be some leaking of the dye, of course, in the lymph nodes. So now we're developing the probes, but we're still injecting quite some amount. Not crazy amount, still close to what's injected in the clinic, but we might, if we're talking about safety, we might want to inject little. And the question is, how little can we go? In other words, what is the biological background that we need to overcome? Yeah, and this biological background will be autofluorescence. So the endogenous fluorophores that will emit upon the excitation of the illumination source you're giving. and it's not well characterized how this tissue background changes upon this longer excitation wavelength. So up to 800 nanometers is pretty well characterized, not really beyond that. So we again go back to astronomy. We got an astronomy camera to image. We needed a high sensitivity camera because if we're going for long exposure times, especially with InGas, you're very obstructed by dark current. And then this one is a liquid nitrogen cooled camera that runs at -190 with a fairly low read noise. Now they're better specs already, but not with that dark current. And then we simply build the setup around. It's a very similar concept, the kind of setup that biologists can build. Again, the diffuse illumination to the sample, some emission filters, lens, and camera. Of course, it's not one emission filter. You have to block the laser, especially for the long exposure times. It needs to be really well blocked, otherwise it reflects and overcomes your image. And yeah. So at 785, we got the results we expected. The liver, the guts, the liver of the mouse, the guts, the bones, all highlighted. The bones here as well. These are known to be autofluorescent structures. However, as we excited longer, these structures here started to highlight. And here, across on top of the sternum, on the neck as well. Actually, I have them at the 1064. The counts, of course, they remarkably, if you look at the scale, they remarkably reduce, as expected, that fewer specimens will be excited, fewer endogenous species. But so you do have less signal in general, but now you have this other signal coming up. What is that? Is it autofluorescence from fat up on 1064? That was weird. Luckily, yeah, my boss had experience in the spectroscopy lab, and then we also have some physicists in the group that raised the hypothesis that it could be Raman, what we were detecting. In a simple wide field setup, basically a photography system, they were detecting Raman. Could that be true? Well, I don't need much introduction to you guys about Raman scattering, but for the sake of completeness, it's when light interacts with the chemical bonds within the molecules, within the tissues, and it exchanges energy to the point that the incident light, for example, in yellow here, will shift its color, its energy, because it's exchanging energy, for example, to the red. And Raman imaging is a huge field. It's very successful with a number of applications, but Raman is a pretty weak process. And this success relies on techniques to stimulate or to enhance the signal of Raman, at least the more bio applications. Well, and because of the stimulation requirement or this enhancement requirement, it's restricted to microscopy because of the high laser powers that you would take a lot of flux to cover, for example, a whole mouse, and very likely be lethal to the mouse, and in inflexible time points. Well, there is spontaneous Raman imaging, light field Raman, that is expandable, or you can increase the field of view to microscopic scales, but to keep detection within silicon, the developers have devised, or scientists have devised as well, systems exciting up to 800 nanometers, but then the Raman shift will be for the Raman shift to be within silicon. But autofluorescence still dominates, and the chemical contrast is still rather low, and the applications are also limited. So this is a Raman spectrum with the fingerprint silent CH and OH regions. And now we adapted a setup. Instead of the long pass filters, we actually have band pass filters that would, so band pass filters for each of these bands. For example, the silent in the silent for, of course, for certain materials will have their Raman shift in the silent region, but not the major biomolecules that you'd expect in the tissue. So that we were using as our metric for autofluorescence, so without Raman. Then CH and OH to start talking about the system. So again, sequential acquisition and then merging the frames at the end. And this is an Eppendorf tube with olive oil on top and water in the bottom. And when we place a filter in the CH, olive oil glows. When we place a filter in the OH, water glows. Merge the images, you get a pretty nice contrast. All labeled free, of course, in a pretty simple setup. We were also able to image the fingerprint region. Of course, now the contrast is optimized for these samples. Now, with a stronger sample, for example, with a stronger A-1 signal, then maybe L-lysine collagen wouldn't be detectable in this range. So, of course, it's a bit complex, but the system just works. And okay, coming back to the long pass filters, these were the images I showed before. And now at 785, we still get pretty much the same signal when we get the band pass in the CH region. But then at 890, it starts to get different. Then 930, 938, then 968, and then 1064. To the point that at 1064, it's pretty much the same image that you're seeing with the long pass or with the band pass. So from this, we kind of conclude that from 892 on, Raman starts to overcome autofluorescence as the major source of tissue background. And these are just the silent region images, pretty much the same image, except for the 1064 that actually falls right, the silent of 1064 falls right into the water absorption bands. So it's really hard to form an image of a very weak process to start with. So now we start to have the laser bleeding through, and yeah, that will need to be filtered. Then some metrics of contrast. So now just some plots, plotting the line across that structure on top of the sternum, showing again that with A92 it starts to be detectable and the contrast increases. Now if we have in green the fat pad, which is a true CH in our idea, and the liver as the autofluorescence, a proxy for autofluorescence in this case, to show the contribution of autofluorescence within the CH channel, and then we can divide these two, and the chemical contrast again increases as the wavelength increases as well. So of course, so chemical contrast increases, but of course at the cost of signal, of intensity. We're losing counts the rather we go. So we need to expose longer. So this is the trade-off to keep in mind which level of contrast, of chemical contrast you need for your application. You will, and how much time can you afford? Now we're still talking about 2 seconds. I think at 890 we started at 10 seconds for one frame. But this is an f2.8 lens that we have in the system, and now we have another camera that will try some much more portable, and there we can use a 1.4, for example, f1.4 lens to have more light throughput, and yeah, we believe we'll increase the speed in at least tenfold and get close to real time, at least with 890 and very likely 940. So that's what next step for us. So this is the results you get. Again, single frames now merged with the colors detaching from each other as you excite longer. some applications. What can you do with it? You can get you can monitor adipose tissue dynamics. The dynamics will come next, but in this case, simply getting the contrast that you could get with MRI, without the resolution of MRI, of course, but in a super simple system and fast, and without the hurdles of having an MRI machine in your animal house or in your laboratory. This was a really cool finding. So this whole mouse, of course, hair is a problem for us. So yeah, we need to shave the mice. So whole mouse, and then the mouse was induced to this MCD diet. It's deficient in a couple of amino acids that induce accumulation of fat in the liver, and we could detect that through skin non-invasively. And then here are the dynamics that I mentioned before. This is a mouse, kind of a well-fed mouse that completely remobilizes its fat depots after fasting, and after you give food, it just builds it up. And you can image the same mouse over time, and just to as an example of which kind of studies you can do, like metabolic challenges and so on. Well, we also used it for tracking tumor growth. In this case, the tumor was actually growing on top of the fat pad, so it's hard to claim that the contrast comes just from the tumor itself, but even having the tumor reach an OH with the CH background of fat, that would be one application, for example, of breast cancer, in which you have a pretty fatty region, and you could differentiate the chemical contrast between fat and water. It's also orthogonal with fluorescence. I mentioned ICG being detectable in the SWIR, but this is even IRFP. So fluorescent protein excitable at 680, 700, also emitting in the above 1100 nanometers. And yeah, there is no crosstalk, and now you can have your fluorescent target and have labels for imaging in parallel. So orthogonal. One application for this imaging system could be quantifying fat in tissues from like freshly from surgery, because you don't need fixation, you don't need staining. Yeah, so you can actually use it for high throughputs also because of the field of view. You can image several samples in one shot. Getting to the end of the applications, then we went to image a more complex sample, an atherosclerotic plaque from a patient. And now we went a bit beyond CH and OH, and we imaged the amide one. Now we endeavored into the fingerprint region and imaged phosphate that we had shown in the beginning, that was highlighted in hydroxyapatite in this band. So we have a visualization of calcification, and of course we validated this, and of lipids and of proteins. This is another sample, another atero sample, and it's pretty stellar. I would say it's very heterogeneous. And the thing is, this is how it comes from surgery, but this is how it looks like after fixation and decalcification, which are the procedures, the steps that you do to send the sample to histology. So you basically lose a lot of information and you interpret information based on host. And yes, it's standard of care, and I'm not claiming that this would substitute it, but it could definitely be complementary to provide staging of atherosclerosis. Yeah, in this case, we aimed to differentiate nerve from fat in a big sample. Preserving nerves is a major goal in surgery, and in some cases it can be pretty hard to see. Here we have an N, so this is a nerve crossing embedded in fat, but the contrast gets pretty increased the moment you image in the OH. Of course, we have all the structures lighting up, and we need to define better bands, but this was a very promising starting point. And you might say, oh, but nerve has myelin. It's reaching CH. And again, we come to the relative scale. Yes, it has myelin, it has CH. Definitely not as much as the whole fat around the tissue. So that's how you get to this kind of contrast. And here, when you overlay OH and CH, and to have an idea of penetration depth and safety of the system, now we put our hands in the setup, and we could see through human skin and even behind. So the signal is coming from a layer underneath the blood vessels as well in the hand. So with that, I get to the conclusion that the shortwave infrared imaging is a promising tool for clinical imaging, for using both label-free and fluorescence-based systems. Approaches, well, the development of novel, brighter, and conjugatable SWIR-emitting materials is surging. In the SWIR, Raman scattering overcomes autofluorescence as a dominant source of tissue background. And the SWIR Raman, macro Raman imaging is a straightforward optical technique that extends chemical imaging to new scales. Yeah, so I would like to thank you a lot for your attention, for our group, led by Professor Oliver Bruns. It's a really nice interdisciplinary group. We rely a lot on collaborations, and like I said, I, as a biologist, wouldn't have come out with the Raman idea, and it was great that Andre was there sitting next to me, and then we started to discuss, and then it was a nice Friday night experiment where, yeah, it was until, I still remember I was chatting at 3 a.m., sending messages to each other. Really cool dynamics in the lab as well. So we are very much looking for collaborations and for people. So if you were interested in collaborating or joining the lab for a visit, for permanent, yeah, feel free to reach out. And thank you so much. Yeah, perguntas em português, claro.
Legal, muito legal o trabalho mesmo. Né? Eu nem imaginava assim. Bom, você tem um ótimo detetor, né, na verdade, para isso. Né? Sem essa câmera, vou chamar assim, ia ser inviável fazer isso. Né?
Não, isso que me surpreendeu muito. Porque agora a gente sabe o que é o sinal, mas aí o pessoal da UCLA estava. Exatamente era esse o problema. Eles tinham um probe. 1064 estação, era um probe mais fraco. E aí eles começaram a ver a gordura com uma câmera de machine vision, uma câmera industrial, mas que eles faziam com a média de 100 imagens, eles começaram a ver mesmo com 100 milissegundos. Então, com uma câmera fácil, uma câmera simples, isso também foi possível.
Então, na verdade, esse ramo deve ser alguma coisa do tipo ramo ressonante já, né? Ou não? Você entendeu? Esse 1064 já é parcialmente absorvido pelo sistema que você tem. Porque para ter um ramo tão intenso assim, né, eu imagino que seja algum mecanismo. E se fosse um ramo convencional, o fato de você sair da região visível para a região do infravermelho, o sinal cai com perda na quarta, isso seria assim, uma perda fantástica. Então, uma maneira de recuperar é alguma coisa. Né?
Sim.
Você concorda que o ramo normal, né, que a gente faz no laboratório, tem uma dificuldade grande de ser coletado. Então, por isso, eu estou tentando imaginar o que tem nessa região que permite você ver com extrema facilidade como você está relatando.
Sim. Eu estou tentando voltar no long pass. A minha interpretação aqui, porque os campos continuam descendo. Então, não é que tem mais sinal, mas mais contraste. A nossa interpretação é que a autofluorescência está caindo. Então, tudo cai, mas a autofluorescência cai mais rápido. Esse é o nosso modelo. A gente cogitou investigar, usar no restaurante, mas a minha compreensão hoje é de que é a espontânea.
Eu imagino que tem algum mecanismo, quer dizer, o fato de você estar deixando de ver a fluorescência, você está deixando de excitar
Claro.
diretamente, mas está indo para a parte de baixo da banda. Quer dizer, você está próximo da banda, você está próximo de uma ressonância, mas não mais vendo o cara. Muito legal, achei muito interessante mesmo. Posso me dar mais uma?
Claro.
Né? E como é que é em relação ao aquecimento? Você tem parte de absorção? Tem algum mecanismo notório de você, depende, você disse que tem alguma coisa da ordem de um sol, não é isso? De intensidade.
Yeah.
Isso promove já algum aquecimento para a amostra? Como é que é?
Para amostras mortas, sim. Para amostras vivas, não. Porque o sangue regula a temperatura. Então, sim, principalmente, por exemplo, na amostra de átero, para entrar na fingerprint, a gente precisou do 1064 laser e aí precisou de 5 minutos de exposição e aí seca a amostra. Então, isso também, a gente tem umas ideias de colocar num vidro para também controlar a grossura do material, da amostra, mas tem aquecimento, mas não em vivo. Em vivo, a única coisa que a gente faz é a gente tira, normalmente tu colocas um aquecimento no camundongo, mas nesse caso a gente tira o aquecimento, monitora a temperatura e a temperatura fica estável.
Você tem show de dedão lá dentro, né?
Não eu, mas...
Já teve alguém lá dentro, né? Foi muito legal. Eu vou daqui a pouco lembrar de outra pergunta.
Claro. Muito obrigado.
Sim. Qual é o tempo típico de exposição para a tua imagem com esse contraste?
Boa. Eu gostei com esse contraste, porque não precisa de todo esse signal to noise. O objetivo aqui era ter imagens bonitas para publicação, para apresentação, e assim posso também baixar pelo menos umas 5 vezes. Então, começa em 10 segundos, acho que o mais curto foi 7 segundos e meio por imagem, e com contraste decente, com 10, mas às vezes eu puxo para 30 só para ficar realmente bonito. Mas quando a aplicação exigir mais velocidade, aí sem dúvida a gente vai ter que abortar um pouco os signal to noise. Mas sim, para 892, por volta de 10, 15, 20 segundos por imagem, para 1064, focando em hidrogênio e carbono, 1 minuto. Mas foi isso. Conseguimos com 100 milissegundos também, em média de 10 imagens, então 1 minuto, perdão, 1 segundo. Também com uma câmera, claro, porque um limitante aqui, que eu falei, porque essa câmera tem um F-mount para as lentes, e aí a gente está limitado no F-number. Então, na abertura da lente. Quando a gente vai para o C-mount, a gente tem uma abertura muito maior, que permite também mais entrada de luz. E essa câmera que eu falei industrial usa a abertura maior já. Então, talvez por aí esteja sendo detectado mais rápido. Então, a gente acredita que acelerar a velocidade vai permitir a aplicação, por exemplo, mais perto da cirurgia, e isso vai não ter impacto que foi a gente recebeu agora já do jornal, e as revisões não foram difíceis, de responder, mas o editor estava meio... o impacto está faltando. E a gente vai fazer rebuttal e tentando aumentar a velocidade com aplicação cirúrgica.
Posso contar, então, para quando você usava a laser, você usava
Sim,
na verdade,
claro.
frente, né?
Eu uso também.
E existe, além dessa perspectiva que você estava comentando, justamente moléculas que sejam longas demais, ou que sejam infravermelho, a gente sempre tem uma colaboração com o grupo que fazia desenvolver justamente corantes aqui no Instituto, né? E realmente sempre puxar para o vermelho é um problema. Né? E você nunca foi pensado em alguma outra abordagem do tipo partícula ou qualquer outra coisa que tenha sido assim, pensado para produzir esse tipo de...
Sim, sem dúvida. E, bom, o meu supervisor veio do laboratório de quantum dots, então a gente trabalha com quantum dots, trabalhou no começo. Ele trabalhou no laboratório do Multiplexed Biomedical, que recebeu o prêmio Nobel no ano passado, e pelo desenvolvimento de quantum dots, claro. Então, e a gente também trabalha com rare earth nanoparticles. Com emissão, aí a gente está puxando mais na parte mais básica, que aí é trabalhando mesmo com 1700, 2000. Então a gente está puxando mais ainda, com essas partículas, puxando mais ainda para o vermelho. Mas também trabalhamos com essa, mas é mais complicado de justificar o potencial translacional, comparado a um corante orgânico. Pelo menos como partida.
E aí eu perguntava, eles não são lábeis, assim, eles não têm um tempo de degradação desses caras.
Degradação...
porque normalmente eles sofrem de falta de degradação também, quanto maior, quanto mais longo, costuma ser mais largo. Não sei, isso que é a minha pergunta.
Na verdade, não. Pelo menos...
Legal.
Não. O Chrome 7, que é o carro-chefe ali, que eu excitava lá em 1980, tá ali a um sol e não degrada.
Degrada. Porque ele entra no plate e depois absorve e foto degrada. Não é só porque isso não sabia que
e, bom, agora pelo lado da química, a gente também desenvolveu um agente de contraste no canal da SED, principalmente porque tem com a ideia agora de fazer a transação, mas não tem equipamento no shortwave, na clínica. Então tá, vamos trabalhar com o que tem, vamos começar por aí. E aí a gente desenvolveu um agente, poderia sim ter usado o WireDye 800, mas fotoestabilidade foi uma propriedade, inclusive, em que o corante novo se sobressaiu.
Mais alguma pergunta? Agradecer.
Muito obrigado.
você está no tempo já.
Sessona agora.
É? Já foi bem rápido, né? Você já trabalhou bastante nisso, né?
Eu acho que eu não sei metade.
Não, é por isso, eu acho que tem. Quer dizer, o laboratório também favorece, né?
Sim. Estou muito contente lá e também